Happy Friday noon, everybody. Hope everyone's having a wonderful day today. Welcome back to class. We were on our Laplace transforms yesterday. We started to make some headway on the inverse Laplace transform. We'll talk about that in more detail today. We'll look through the different scenarios that we can have in terms of inverse Laplace transforms by partial fraction expansions, but we'll just kind of go over and review the material that we have in that particular area so that we can ensure that we understand exactly what it is that we're doing. And so there's the bell and it's time to go. So let me start with a piece that I told you yesterday. I just wanted to double check some mathematics. So this is what we ended up with yesterday. So this is just sort of a recall from previously. This is with regard to, we were looking at some properties and then we were doing a particular example of a Laplace transform that's important to us. So we were looking at the Laplace transform of t raised to the n power e to the minus at, because we have lots of times we have these t multiples of e to the minus at, and the standard t multiple that we have, believe it or not, is we usually have a t or a t squared, but nothing more than that. And when we looked at that, we said, well, that Laplace transforms into n factorial 1 over s plus a to the n plus first power. And there are a number of ways that we can look at this. So the first thing we can do, if we want to, with this, is we know that n factorial is just a constant. So I can divide both sides of this transformation by that constant. And if I do, we'll have the following: t to the n e to the minus at divided by n factorial. Laplace transforms into 1 over s plus a to the n plus first power. And so that's a great way to look at it. So right now we have two ways to look at this Laplace transform. They're both great ways to look at it. But even these two forms are not the general form that we will see and view. Normally when we utilize this form, we're utilizing this form in the inverse. And so that means we're looking at this side of the equation, which is the right-hand side of the equation, and we're trying to write what the left-hand side of the equation is supposed to be. And when we see that right-hand side of the equation, usually we don't see it with an n plus 1 in the numerator, we just see it with an n, like if it's the number 3 or the number 5. So one of the things that we can do is we can replace n plus 1. If I define, for example, a new variable, let's call it m, and let's let m be equal to n plus 1, then n is equal to m minus 1. And so now let's replace all the n's with m's. This is like doing a u substitution. So if we do that, we'll have from the first equation, t raised not to the n power, but raised to the m minus first power times e to the minus at. And that's going to Laplace transform into n factorial is m minus 1 factorial. And then that's going to be times 1 over plus a. And this is the n plus first power, but n plus 1 is equal to m to the m power. And that's what we actually like. We like on this side, we want just the function in the S domain raised to a particular power. And so in your mind, you can see this as an M or you can see it as an N. It doesn't matter. So right now, I could replace all of these by N's. It doesn't matter. It's just a dummy variable that we're using here, even though it's a constant value. That can be an N and that can be an N like that. So t to the n minus 1 times e to the at, the minus at is going to transform into n minus 1 factorial times 1 over s plus a to the n power. Well, the problem again is that normally we just have 1 over s plus a to the n power in the frequency domain. So this is what we want to look at. 1 over s plus a to the n power inverse Laplaces into t to the n minus 1 e to the minus at over n minus 1 factorial. So we're going to have these kinds of things, and we're going to want to know what the inverse is. So this is a nice way to look at it as well. And so I just wanted to go back through that. I put a little hold on that. I wanted to double check my math and make sure I didn't make a math mistake and everything was good. The math was fine. So those are ways of looking at this inverse Laplace transform, is just looking at this fraction, which we're going to see today in the partial fraction expansion. So let's now go back to partial fraction expansion and what we're doing. So partial fraction expansion is about expanding a strictly proper rational fraction. What does it mean to be strictly proper? We talked about that. It means the order of the numerator is lower than the order of the denominator. So when we're talking about a proper rational fraction, we're talking about the fact that a fraction f of s, first of all, a rational fraction is a fraction of two polynomials. Let's write it like this. A sub n, s to the n power, plus a sub n minus 1, s to the n minus 1 power, plus dot, 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 plus a1s plus a0. And then in the denominator, I'll write b sub m, s to the m power, plus b sub m minus 1, s to the m minus 1 power, plus dot, 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 plus b1 s plus b0. And oftentimes you'll see in the textbooks that this is written the following way. It's a numerator polynomial divided by a denominator polynomial. We said one of the things that we're going to want to do in this world is to ensure that this is strictly proper. So for this to be strictly proper, it means that n must be less than m. The order of the numerator must be smaller than the order of the denominator. That was one thing we said. The other thing we said is, gosh, we don't like that denominator at all because we like the lead coefficient to be 1. So we can factor out a b sub m. I know this is going to look a little ugly, but don't worry about it. So the way we factor that out in this denominator is the following way. This is equal to b sub m times s to the m power plus b sub m minus 1 over b sub m, s to the m minus 1 power, plus dot, 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 plus b sub 1 over b sub m, s plus b0 over b sub m. And that is the same exact thing as this up here. It's the same thing. This b sub m is a constant in the denominator, and what we did yesterday is we said, well, look, just take that constant and put it up in the numerator like this. And there we go. And now we have a denominator in the bottom whose lead coefficient is 1. And that's what we're after. Why are we after that? Because we're trying to factor this, and we want this to be factored in terms that look like the following. So this would be this part here. We can factor that. S minus P1, S minus P2, S minus P3 times S minus P raised to the, how many poles are there? Well, the order of the denominator is m, there are m poles. So it's factorable into all of those terms. Why do we want to factor it into those terms? Because if it's factored into those terms, we know how to do partial fraction expansion based on what partial fraction expansion is. So let's now jump forward with kind of where we ended up the last time. So we looked at case number 1 for partial fraction expansion. And case number 1 is simple real poles or real roots in the denominator. Remember, a pole is a value of S that causes the denominator to be equal to 0. You can also think of a pole as a value of S that causes the fraction f of S to be equal to infinity. Because if you have a 0 in the denominator, then anything divided by 0, unless it's 0 divided by 0, anything divided by 0 is infinity. So these simple real poles mean that the power of each term, 1 to the first power, they're all to the first power. That's what makes it simple. And the real pole means that the p's are real numbers. Normally for us, we have things that look like this in our denominators: s plus 3, s plus 2, okay? In this case, p1 equals minus 3. In this case, p2 is equal to minus 2. So remember that the p-values are the values of s that cause the denominator to be equal to 0. And so this is where it looks like is a plus 3 for the pole, but the pole is not. The pole is minus 3. Okay, so I think we wrote an example the last time. So let's look at this example. Let f of s be equal to 8s plus 19 divided by s squared plus 5s plus 6. And we know that, first of all, the denominator can be factored, and we always like the denominator in factored form. Doesn't matter with the numerator. In fact, it's better that the numerator often is not. This satisfies simple real poles. When it satisfies simple real poles, the partial fraction expansion is the following. I'm just going to write this on this side. I know it's f of s. S plus 3, S plus 2, and it's going to be equal to a constant. You can call your constants whatever you want to. Your textbook uses K1, K2, K3, K4. You can call them whatever you want to. Right now, I'm going to use A and B and then C and then D. A over S plus 3 plus B over S plus 2. All you have to decide is whether you want A over S plus 3 or you want A over S plus 2. Doesn't matter what you put A over, just make sure you know which one it is. So now for us, our task at hand is to find the A and B. I'm going to put either Connor and or Jack on the spot here. I want you to tell me how you solved for A and B in your differential equation class. What process or technique did you use?
So we would try and get a common denominator. So we would times A by S plus 2 and B by S plus 3.
Okay, so that was what I showed you. Now I'm going to show you what smart engineers do. And I hope all of you can appreciate how smart engineers are. So I want you to observe this equation. And now I'm going to show you how what we can do is, so we want to solve for A and B. And the process that Jack is speaking of, and I'll write it down at the end if you remind me to show you again the process that he's using, because it is a handy process. There's nothing wrong with it. But the process that I'm going to show you allows you to solve for A individually and B individually. And Jack's process would require 2 equations and 2 unknowns. If we had more denominator terms, 3 equations and 3 unknowns, 4 equations and 4 unknowns, 5 equations and 5 unknowns, and that is hectic. So we have a process that allows us to solve for A directly without bothering with B. And I'm going to show you the way it works through this example. So what I'm going to do is, when I want to solve for A, I am going to multiply both sides of this equation by A's denominator. So I'm going to start, and I'm going to solve for A. And so what I'm going to do is, step 1 is multiply both sides of the equation by the denominator of A. So that means multiply both sides of the equations by s plus 3. Here we go. You ready? 8s plus 19 divided by s plus 3 times s plus 2 times s plus 3 equals a over s plus 3 times s plus 3 plus b over s plus 2 times s plus 3. I know you're all sharp and you recognize that that cancels with that and that cancels with that. And so what I'm left with is 8s plus 19 over s plus 2 is equal to a plus b times s plus 3 over s plus 2. Now, even if there are more terms on the right-hand side of the equation, if there were more terms, I'm sure you can agree that all of them would have in their product, they would be multiplied by s plus 3. Because I multiplied the entire equation by s plus 3. I know we don't have them here, but all of them would be multiplied by s plus 3. So if I take both sides of this equation and evaluate when s is equal to minus 3, then all of these other terms that we have will be equal to 0. Does everybody see that and understand that? Because they all have an s plus 3 term, so I look at, I'm solving for a, I multiply through by a's denominator, and then I let a's denominator be equal to 0. So notice how all the other terms over here will disappear, they'll be 0, and I have a that's left by itself. And so this would tell me that 8s plus 19 over s plus 2, evaluated when s is equal to minus 3, is equal to a. All right, well, let's put that in. 8 times minus 3 plus 19 divided by minus 3 plus 2 is equal to a. A equals, in the numerator, minus 24 plus 19, that's minus 5, divided by minus 1. A is equal to 5. And so notice how that had nothing to do with B. B didn't get in the way of solving that problem whatsoever. So that's A's value. To solve for B, we do the same exact thing, except we multiply by B's denominator. So when we're solving for B, 8s plus 19. So we have 8s plus 19. I'm going to step through the entire thing so you see it again. S plus 3 times s plus 2 equals a over s plus 3 plus b over s plus 2. And I'm going to multiply both sides times s plus 2. So to solve for b, I solve by multiplying through by b's denominator. I think you can see that when I multiply by b's denominator, this is what's going to happen. On this side, the s plus 2 will disappear, and I'll end up with just an s plus 3. Over here, I'll have a times s plus 2 divided by s plus 3, and then b gets isolated by itself. Now when I take this and I evaluate this when s is equal to minus 2, that term will go to 0. And so b is going to be equal to 8s plus 19 divided by s plus 3, evaluated when s is equal to minus 2. And that is 8 times minus 2 plus 19 over minus 2 plus 3, which is equal to 3 over 1, which is equal to 3. So we now have the values of A and B. So just a reminder, A equals, we had up here was the 5, and B equals, here we have the 3. A equals 5, B equals 3. So this is what I claim. I claim that therefore, f of s, which was equal to 8s plus 19 over s plus 3, s plus 2, is equal to 5 over s plus 3 plus 3 over s plus 2. That's what I claim. in partial fraction expansion. Now you can use Jack's method. Let's use Jack's method and verify that in fact that is true. So what Jack said is form a common denominator over here, s plus 3, s plus 2. And now in the numerator, it's going to be 5 over s plus 2 plus 3, not 5 over, 5 times s plus 2 plus 3 times s plus 3. And we want to check and see, hey, is that equal to 8s plus 19 over s plus 3s plus 2? Well, look, the denominators are the same, so what must be true if these are equal? What must be the same?
The numerators must be equal.
Correct. So let's check the numerator. So I have 5s plus 3s, there's my s terms, plus 5 times 2, 10, and plus 3 times 3, plus 9. Let's see, 8s, plus 19, plus 19. Check, it's equal, indeed. And so here's the shorthand notation that we write. And so go back to the beginning. So f of s equals 8s plus 19 divided by s plus 3 times s plus 2. And we say it's equal to a over s plus 3 plus b over s plus 2. We know the process. We know what we're going to use. We don't have to write it out. We're going to do the same thing every time. Multiply both sides of the equations by s plus 3, evaluated when s is minus 3. Then to solve for b, multiply both sides by s plus 2, and then set s is equal to minus 2 to solve for b. This is how we write it. A equals s plus 3 times f of s, evaluated when s equals minus 3. B equals s plus 2 times f of s, evaluated when s is equal to minus 2. So this process works for us all the time, provided this is a strictly proper rational fraction. You can do this. If this fraction is not strictly proper, you can do this. This is what I was telling you. My mistake is I did something like that. Here's an example. An example of a mistake. So in this mistake, we get, let's say we have 8s cubed plus 19 over s plus 3 times s plus 2. Let's say that that's f of s. So I'm going to say, well, that's equal to a over s plus 3 plus b over s plus 2. So a equals s plus 3 times f of s, evaluated when s equals minus 3. Well, that's equal to 8s cubed plus 19 divided by s plus 2, evaluated when s is equal to minus 3. Notice this is everything I started with. I'm just getting rid of a's denominator. See, I multiplied by s plus 3, so I'm getting rid of a's denominator. That's all we're doing. So plugging the numbers in, doing this blindly, we have no idea we're doing anything wrong at all. 8 times minus 3 cubed plus 19 divided by minus 3 plus 2. Okay, and I don't know if I feel like doing that multiplication, but that's clearly equal to some number. Wrong, it doesn't work. And the reason it doesn't work is because this part right here is incorrect. This is not a strictly proper rational fraction, so I have to do the long division first and then get the remainder part that's the rational fraction. So must be strictly proper. But notice how there's nothing in the math work that fell apart that told us we were doing anything wrong. Nothing here said anything was wrong with what we were doing. Nothing. We'll get a number, and then you can blindly put that number in, but that is not a partial fraction expansion of that polynomial f of s. Okay. So here's a summary of what we do with simple real poles. So for each simple real pole that we have in f of s, we know there's a corresponding term in its partial fraction expansion. There is a corresponding, whoops. So there's a corresponding term that looks like the following. A over S minus P. Okay, so we're gonna have a term where we can find the A value, where A is equal to S minus P times F of S, all evaluated when S is equal to P. And the best part, which we didn't even talk about, and its inverse Laplace transform. That's what we're doing all this for. Is A e to the PT. This is the most common term we will see in everything that we're doing with. It's the most common term, an exponential form with a multiplier that is a constant value. Okay, so I would encourage you to use this process to solve for the values of A and B. They are much faster. They will get you the answers quickly. And when you start to have 4 and 5 and 6 terms in the denominator, you're going to be hard pressed to solve for all of your constants. You'll be hard pressed. Okay, let's just, I'm going to, on the fly, I'm going to make up another example to make sure we have. So in this example, let's let f of s be equal to 10s squared minus 3 divided by s plus 1, s plus 2, s plus 3. Well, that satisfies, we are definitely in case 1. I have simple roots, and they are real in the denominator. And so we know by partial fraction expansion, this is A over s plus 1 plus B over s plus 2 plus C over s plus 3. And we know that A is equal to s plus 1 times f of s evaluated when s is equal to minus 1. And that's equal to 10s squared minus 3 divided by s plus 2 times s plus 3, all evaluated when s is equal to minus 1. Now let's put in the minus 1. 10 times minus 1 squared minus 3 divided by minus 1 plus 2 minus 1 plus 3. This is equal to numerator 10 minus 3, 7, denominator 1 times 2 equals 7/2. B is equal to s plus 2 times f of s evaluated when s is equal to minus 2. That's going to be equal to 10s squared minus 3. Notice the denominator never changes. It's just, I'm sorry, the numerator never changes. It's just the denominator. This time the denominator is s plus 1, s plus 3, because I'm multiplying through by s plus 2. So that term in the middle there disappears. And so this is all evaluated when s is equal to minus 2. So let's see what happens there when we evaluate that. When we plug in minus 2, 10 times minus 2 squared minus 3 all over minus 2 plus 1 minus 2 plus 3. In the numerator, we have 10 times 4, 40 minus 3, that's 37. And in the denominator, I have minus 1 times 1, so over minus 1, this equals minus 37. So there's 2 of our constants. And then the third one, C is equal to S plus 3 times f of s, evaluated when s is equal to minus 3. And that's equal to 10s squared minus 3 divided by s plus 1, s plus 2, evaluated when s equals minus 3. And that's equal to 10 times minus 3 squared minus 3 divided by minus 3 plus 1 minus 3 plus 2. That's equal to 90 minus 3, 87, divided by minus 2 times minus 1. There it is, 87 halves. Don't even have to do anything with it. 87 halves. So what does that mean? F of s is equal to A, 7 halves over s plus 1, plus B, which is a negative 37. I can leave the plus there and put minus 37 in the numerator. Or I can put the minus out in front, it doesn't matter, over s plus 2, plus 87 halves over s plus 3. Therefore, f of t equals inverse Laplace of that, 7 halves e to the minus t, e to the minus 1t, minus 37 e to the minus 2t, plus 87 halves e to the minus 3t. That's what we're going to be doing. From our circuits, we're going to get functions that look like f of s. We're going to do partial fraction expansion. We're going to solve for the values. And then we're going to do the inverse Laplace transform by what? I didn't use any integrals to do the inverse Laplace transform. By recognition, I recognize these forms. That's why that lookup table is so important. And in that table, we know that anything that looks like e to the minus at has a Laplace transform of 1 over s plus a. And that's what all three of these look like, a constant over s plus a. The constant is just the multiplier. That's the property of the Laplace transform. That's the multiplier property. The multiplier property. Okay, let's do one more, and then we're going to move on to our second case. So we know that this is going to partial fraction expand into a over s plus b over s plus 2 plus c over s minus 3. Now in your circuits, unless you have an op amp or some other active device, you're never going to get a negative like I have here from your circuits. But this is just doing the math, so let's do the math. A equals s times f of s, evaluated when s is equal to 0. That's equal to s squared plus 2s plus 1 divided by s plus 2, s minus 3. Evaluated when s is equal to 0, that's easy. That's 1 over minus 6. So there's our A. A is 1/6. A equals 1/6. Just box that up for a moment. Let's find B. B is s plus 2 times f of s, evaluated when s is equal to minus 2. So that's going to be equal to s squared plus 2s plus 1 divided by s minus 3, evaluated when s is equal to minus 2. Let's plug that in. That's going to be 4 minus 4 plus 1 divided by minus 2 times minus 5. So 4 minus 4 cancels. That's 1 over 10 equals 1/10. So there's A, there's B, and now I just want to find C. So C is equal to s minus 3 times f of s, evaluated when s is equal to positive 3. And that's equal to s squared plus 2s plus 1. Numerator is the same every single time. The denominator differs. This time it's s times s plus 2. That's evaluated when s equals 3. All right, 9 plus 6 plus 1 divided by 3 times 5. So that's 9, 10, 16 over 15. Beautiful. F of s equals a minus 1/6 divided by s plus b 1/10 divided by s plus 2 plus c plus 16/15 divided by s minus 3. What's the inverse Laplace transform of this first term?
Negative 1/6.
One more piece. Negative 1/6 times. That's the constant. What's 1 over s? What's the inverse of 1 over s?
E.
Not e.
It's u of t.
That is correct. U of t. What's the inverse of this one? There's the 1/10. What's the rest of it? So think of the 1/10 as being out front here, and now I have 1 over s plus 2.
E to the negative 2t.
Well done. E to the minus, nope, not this time. I have a negative in there, so this is a positive 3t. And we won't see too many of those. And in general, when it's positive, we don't even write the positive number in there, e to the 3t. Why do we not see those? Because in a circuit, that thing is blowing up. I don't think we're going to run into too many currents or too many voltages that are going to go to infinity. So usually they're decaying away. Okay, that is case number 1. The second and third cases are a little bit more challenging to work with, but not overly difficult. So let's talk about a simple pair of complex conjugate poles. We know we can get complex roots. So, simple pair of complex conjugate poles. What does that mean? A simple pair? I'm going to have s minus p times s minus p conjugate, where in general, p is complex. P is alpha plus j beta, and that means P conjugate is equal to alpha minus j beta. While we're on this, I just want to make sure we are familiar with something that I don't know that we've spent a lot of time on it. I don't think we have. So let's be sure we know right now. When we take a complex number, So P is a complex number. So if I look at, so this is just a little aside, and then we'll get back to case number 2. If I look at adding, what happens when we add a complex number, P, plus P conjugate? What happens when we do that? Well, this is equal to alpha plus j beta plus alpha minus j beta. Plus or minus j betas disappear, and this is equal to 2 alpha. So the way we write this is the following. So when we have P plus P conjugate, this is 2 alpha, but alpha is the real part of P. So for any complex number, when I add the complex number to its complex conjugate, it's twice the real part of that complex number. You can probably see there's a similar thing that happens when I subtract. So let's see what that does for us. Alpha plus j beta minus alpha minus j beta. So I'm subtracting the difference between the complex conjugates. Look at this time, the alpha parts disappear, and this is equal to j beta minus a minus j beta. This is j times 2 beta. And so this is twice the imaginary part of P. So this, what we have, is equal to P minus the conjugate equals j times twice the imaginary part of P. Okay, so those are nice results, worth knowing, just some of the mathematical beauty that we have when we deal with complex numbers. A lot of times we don't think of things as being beautiful, but let's just understand that there are some nice things that happen. Okay, so now what I'm going to do is this. I'm going to just focus on only complex conjugate roots. So in other words, f of s could look something like this. It could look like this. S plus 3, S plus 4, plus 2j, S plus 4 minus 2j. Okay, so that could be its denominator. I just want to focus here. Don't worry about this. We already know how to handle S plus 3. Let's just focus on the complex conjugate part and what happens there. Now, does anybody know why the focus is on complex conjugate pairs? Why not just a single complex root? Anybody know that? So we're focusing on complex conjugate pairs. Notice we didn't write something like this. F of s is s plus 3 times s plus j. So there's only one complex term in the denominator. We didn't do that. We put them as complex conjugates. If I have s plus j, then I better have s minus j. The answer is because we live in the real world, you're never going to get just one complex term. It'll always come with its complex conjugate. Remember where these roots come from. They come from factoring the polynomial. In the polynomial, I wasn't real clear, so let me be clear right now. In those numerator and denominator polynomials that we talked about way back at the get-go, the n of s and the d of s, right here, these coefficients, all the a's and all of the b's are real. All of the A's and all of the B's are real. So if they are real, you cannot have complex conjugate factors. They will only factor into roots that if they're complex conjugate, they can't exist by themselves. They must have the complex conjugate. So if you have complex factors, you must have the complex conjugate. So they will always appear in pairs, okay? Always in pairs, never just by itself. So let's focus on just the pairs. So let's assume with me that we have the following, that f of s looks like, in the denominator, s, I'm going to write it this way, s minus alpha minus j beta, and s minus alpha plus j beta. So P1 equals alpha plus j beta, and P2, which is P1 conjugate, is equal to alpha minus j beta. That's what we said before. I don't care what the numerator is, blah, 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 but as long as it's strictly proper. So we can expand this. So partial fraction expansion still works. It is A over S minus alpha minus j beta. But here's where we get lucky. I'm not going to do a proof for you, but when we have complex conjugate roots in the denominator, the numerators will be complex conjugate constants. So what's the beauty of this? I have two terms, but how many of these numerator terms do I have to solve for? How many numerator terms do I have to solve for?
One.
That's right. You just solve for one. Once I have A, I immediately have A conjugate. Once I have A conjugate. So following our rules, and let's, for argument's sake, let's assume that we know what this numerator is for f of s. So we're expanding this, and now what we can say is f of s is equal to, sorry, I wrote it already here, right above me. So this is f of s. There's my partial fraction expansion. So A is clearly equal to S minus alpha minus j beta times f of s, whatever f of s is, I haven't written it completely in, but it is evaluated where s equals alpha plus j beta. And this is where the math gets ugly. Because now, instead of plugging in just real numbers, we're plugging in complex numbers into this equation. But don't worry about it. We're going to do it, and we have it. A conjugate, you can probably see why it is a conjugate, because it's S minus alpha plus j beta times f of s. But we're going to evaluate everywhere where S is equal to alpha minus j beta. And one of the things I'm going to point out to you, because there are a couple of different ways to work with complex numbers. This is one of them. I want you to notice that I put the A, not the A conjugate, over the term, most important, that is the minus with the J term. A over the term with the negative J. Remember that. Okay. So we know that the coefficients of the polynomial f of s are real. So we know that. So that's why A and A conjugate will turn out to be conjugates of each other. Now, so assume we have these values. It's A conjugate. I have the values. Let's look back right here. And I want you to tell me now what f of t is, knowing the values of A and A conjugate and their complex. So what's f of t? What's the inverse of this term? Well, don't forget, if we have any constant, K over S plus A, the inverse Laplace transform is K e to the minus AT. All right, well, let's look at this and let's put that in that form. Here's the A out in front. S plus, this alpha, there's J beta. Okay, that satisfies that form. What's the inverse? I have this, there's its inverse. I want this. This looks just like this. What's its inverse?
Can be AE to the alpha plus J beta.
Well done, Jack. Times T. AE to the alpha plus J beta times T. Okay? And so then the other term is going to give me a conjugate E to the alpha minus J beta times T. Notice two things. This whole thing is the complex conjugate of this, and this is the complex conjugate of this, which means that this is the complex conjugate of that term. That's what that means. Those are complex conjugates of each other. Well, using our property, so let's state that. This is term number one. This will be term number two. 1 and 2 are complex conjugates of each other. And I'm adding them. And we are adding them. So the result twice the real part of A e to the alpha plus J beta T. It's either this, so I'm treating the first term like the first term is P, where I showed you P plus P conjugate. This is my P. So it's twice the real part of P. That's got to be the P. Otherwise, it is also equal to, if this is my P, it's twice the real part of a conjugate e to the alpha minus J beta T. I don't want to focus on that. Let's just focus on this one right here. Okay, we don't know a lot about A, but we do know that in general, A is complex. Remember, in general, A is complex. Why is that important? Because if I'm taking the real part and this is complex, it affects how I take the real part. So let's assume that A is magnitude of A, e to the J theta A. So it's a complex number, and I can write any complex number in its exponential form. So I want to use that exponential form. Magnitude and its angle. And we know how to find the magnitude and the angle, by the way. We know how to do that. As long as we know A, it doesn't matter what form A is in, we can find it. Great. So now let's go back and rewrite this. So f of t is equal to twice the real part. Now I'm substituting for a, magnitude of a, e to the j theta a times e to the alpha plus j beta t. Okay. What interesting things can we do with this function that we now have, with this, everything that's inside of here? Is there anything that can be pulled out of the real part? In other words, it's real, so it doesn't matter if I leave it inside or I pull it out in front. What about the magnitude of A? Is that a real number?
Yep.
It sure is. So I'll start with that. Twice the magnitude of A, and then the real part of, now what I have is I have some exponentials that I can combine together. And so what I'm going to do is I'm going to separate and combine. So here's the separation. E to the alpha t. Does everybody see the e to the alpha t? That comes from that with that. But there's still an e to the j beta t. But over here, there's an e to the j theta a. So e to the j, I have beta t plus theta a. Take a look at that math. Convince yourself that I did that correctly. So I have all of the terms. I've just written them in a slightly different manner. What about e to the alpha t? Well, remember, alpha and beta are real numbers. E to the alpha t, real? Can I pull that out of the real?
Yeah.
Yeah, can pull that one out. Now, what is the real part of a purely imaginary exponential? What's the real part? Don't forget, Euler's identity, e to the jx equals what? What is the real part? What's the imaginary part? What's the real part of e to the jx?
Cosine x.
Excellent. What's the imaginary part of e to the jx? I know we don't want the imaginary part. What's the imaginary part of e to the jx?
Sine x.
Excellent. Don't ever forget that. Euler came up with this great relationship for us to help us solve these awesome problems. So it's cosine of, there's my x. Whatever multiplies the j, e to the j, boom, that's the x. So what do we have? We have, when we have two complex conjugate terms that are in the function f of s, when we have two complex conjugate terms, let me see if I can pull them down for you. There they are, two complex conjugates. We're going to group them together, solve for just one of the numerators. Once we have one of the numerators, make sure it's the numerator that goes over the term with the negative sign. Because if it doesn't, then we have this positive sign, which gives us a negative in the cosine. And we've got to change some things. So make sure it's the term that goes over the negative with the j part. And those two together have an inverse Laplace transform, which is this form. Twice magnitude of a, e to the alpha t, cosine of beta t. Okay? Now, we'll do an example when we get back from break in which we can see this in action, and we'll make some notes, and then we'll continue to move on. So let's go ahead and take a 5-minute break. I'm going to put our recording on pause. Let's take a 5-minute break and come back in 5 minutes. Okay, we're back on the air. Any questions so far on some of the work that we're looking at right now with regard to these inverse Laplace transforms through partial fraction expansion? For example, let's start first with case number 1. Is that process easy enough to understand? Just using this multiplying through by its denominator, it causes all your other terms to be equal to 0 so that we can isolate the numerators very quickly. First of all, do you like that? Jack, Connor, do you like that a lot better than the process you used before?
Yeah, that works for me.
A little faster?
Yeah, for sure.
Yeah, for sure. I'm not sure why they don't teach in math classes. I really don't understand that at all. There's got to be a method to their madness, but it is obviously a much nicer method. And when I saw that, I knew what we had learned in both differential equations. Learned it also in the Calc 2 course. I think it was when we first covered partial fraction expansion. I'm not sure why they don't cover it that way, but nonetheless they don't. So that begins an easy process. Now what we're looking at is for complex terms, we can use the same exact process. So there are 3 different ways we can go through these partial fraction expansions. The question is, do you want to do the same challenging work over and over again, or would you rather boil it down to, I know exactly what's going to happen. I'm going to get something that looks like some constant multiplied by e to the alpha t multiplied by the cosine of beta t with a phase shift. That's the question. If you're looking at this, still sitting on the tablet here, you'll notice that this term right here, do we or do we not know the Laplace transform of that function? There's a handful of Laplace transforms that we have, and we're going to have our table of transforms, that lookup table. We just quickly look things up. By the way, if you look in the CRC tables, like you pull that book over, there's a ton of nice transforms. Great resource to find Laplace transforms. So the answer to the question is no, we don't know that Laplace transform. We know the Laplace transform of cosine of omega t, or in this case, cosine of beta t. But when we put a phase shift in there, we don't know what happens to the Laplace transform. We don't have that as one of our lookup items in our table. So getting to this form is really nice, but it comes in a roundabout way without us previously knowing that this was the Laplace transform of some functions that we were going to uncover. So I find that particularly interesting. So let's continue forward with where we're at by looking at how we use this. Okay, so how would we use this? Well, let's look at this example. Let's let f of s be equal to s divided by s plus 1. And normally what you see when they're left in factored form is you see this. S squared plus 2s plus 2. Now, we can factor that. In fact, let's go ahead and do that. So it's going to be s plus 1, s plus 1 plus j, and s plus 1 minus j. And if you're wondering how I got that, don't worry. If you don't know how to factor them quickly in your head, just utilize the quadratic formula. It will always get you the answer. Okay, partial fraction expansion says that that is a over s plus 1 plus b over s plus 1 minus j. Notice I'm selecting the minus under my b plus B conjugate of S plus 1 plus J. So those are our three terms. Okay, so what do we do with that? Well, we start to find those values. The easiest value to find is K1. I'm sorry, K1, A1, right here. So A is equal to S plus 1 times f of S, evaluated when S equals minus 1. That doesn't change. It's still a simple pole. It's a simple pole. So we follow the same rules. It's a simple pole. All right, well, let's see what that is. It's this fraction here without S plus 1 in the denominator. S over S squared plus 2S plus 2, evaluated when S equals minus 1. It's equal to minus 1 divided by minus 1 squared plus 2 times minus 1 plus 2 equals, you can see minus 1 in the numerator. That's canceling in the denominator, divided by 1. And so all that is equal to minus 1. So there's our A. Now from here, we could do a lot of things, but I'm going to leave it just the way it is because this is a beautiful thing. And I'm going to solve for B. So continuing along, B is equal to S plus 1 minus J times f of S, evaluated when S equals minus 1 plus J. Great. Let's see what that is. Well, first of all, it's S divided by, well, the S plus 1 is still there. Now, when we look up here, I can't use this because one of the factors in there is this one, and I'm multiplying through. So we're going to cancel that factor, and I'm left with this one here in the denominator. So that still leaves S plus 1 plus J. I'm going to evaluate when S equals minus 1 plus J. Okay, you can see by looking at this that the mathematics involves complex numbers. Don't let complex numbers phase you one bit. So let's see what this is equal to. So it's going to be minus 1 plus J divided by minus 1 plus J plus 1, and then minus 1 plus J plus 1 plus J. Numerator, minus 1 plus J. Denominator, let's see, I have that cancels with that. So that gives me a J. Over here, that cancels with that, and that gives me a 2J. And so in the denominator, J times J is minus 1, so it gives me a minus 2 in the denominator. I'm going to take the minus, and I'm going to bring it up top. Okay, so that minus came from the denominator. I just brought it up to the top. So that's equal to 1/2 here, and then 1 minus J. This is one of the nicest numbers that we'll ever run into, and 1 minus J is square root of 2 at an angle of negative 45 degrees. So that means the magnitude of B equals root 2 over 2. And theta B is equal to an angle of minus 45, so it's minus 45 degrees. That's what theta B is. So we're done with finding the values of the constants. We have A, we have B. So we have the values of the constants. Therefore, we know for our partial fraction expansion, so we know that f of S is equal to, well, first it was A over S plus 1, remember that. A over S plus 1, and A is minus 1, so let's write that. So it's minus 1 over s plus 1. Now it's plus b, and b is root 2 over 2 at an angle of minus 45 degrees. And that's divided by s plus 1 minus j. So then I'll have root 2 over 2 at an angle of positive 45 degrees. That's the complex conjugate. In case we haven't covered, did we cover that before? The complex conjugate in rectangular form means change the sign of the j term. The complex conjugate in polar form means change the sign of the angle from positive to negative or from negative to positive. Magnitude stays the same. Okay, these two we're going to group together. So let's see what we get. So f of t equals, from here, minus 1. I know I don't have to write the minus 1, I have to write the minus, e to the minus t, e to the minus 1t, e to the minus 1t. Now here, remember, alpha here is negative 1. The pole is negative 1. And beta, so this is alpha, and beta is equal to positive 1. So don't forget that from this. Alpha is negative 1, beta is positive 1, and we're taking it from the first term, because that will align with this angle. So what do we have? Well, we said that all of that inverse Laplaces into 2, remember that term? 2 times the magnitude of the constant. The magnitude of the constant is root 2 over 2. Times what? Times the cosine of beta. What's beta? Beta is 1 plus the phase angle. Minus 45 degrees. Just cleaning this up, f of t equals negative e to the minus t. I'm sorry, I missed a term, I need my e to the alpha t, I'm going to put that at the end. Normally I like it in front of this, times e to the minus 1t. Normally I like this right in here, and I'll write it that way here, plus twice e to the minus t cosine of t minus 45 degrees. So that is the inverse Laplace transform of that term.
Shouldn't it just be the square root of 2 instead of 2?
Thank you, square root of 2. Thank you very much, Connor. Appreciate that. I always appreciate when you watch the math and catch my mistakes. Square root of 2 it is. So notice how what we did is we didn't find this value, then do the inverse of this term, find this value, do the inverse of this term. We found this value, and then we said, great, once we have the value, we know the inverse of that box. And that is a much nicer way to do it, to find the inverse of the box versus finding the inverse of each of those individual terms. Okay, I'm going to show you with this same example in alternate partial fraction expansion. And Jack and Connor, I'm not sure if you've seen this, but here's an alternate approach when you have complex conjugate roots. And you'll see why people like this one. I didn't like this up front because I don't think I was really sure of myself, but I tend to use this one more than I use the others. And so same function, f of s, it's equal to S divided by S plus 1, S squared plus 2S plus 2. I'm not going deep into mathematics, but if you know anything about partial fraction expansions, we can do the following. The numerator is always 1 power lower than the denominator. Always 1 power lower. So I can do this. This is a way of avoiding the complex numbers. If you don't like working with complex numbers, this is a better approach. So K2S plus K3. I'm using K's, I could use A's, I can use B's, I can use whatever I want. K1, we can still solve exactly the same way. And so I would recommend that you do, obviously. So K1 equals S plus 1 times f of S, evaluated when S is equal to minus 1. We've done that already, and what did we end up with before? Minus 1, right? From previous work. Okay, now the question is, how do we deal with this? Because we can't multiply through by S squared plus 2S plus 2 and then set S equal to a number. That doesn't work for us. And so here is the process that Jack had talked about earlier about forming the common denominator is what is most widely used. So we form the common denominator by doing this side. So for S plus 1, S squared plus 2S plus 2 equals. K1 we already know, so put it in. 1 over S plus 1. Okay, but now with this, I'm going to form this common denominator. So I'm going to take this minus 1 and I'm going to multiply by S squared plus 2S plus 2. The rest of that numerator is plus S plus 1 times K2S 3. So this is one way to solve this. There are many ways to solve this. This is one way, and this is called, it's called the common denominator approach, where we set the numerators equal to each other. So we can forget the denominators right now because we know they're the same. Therefore, S must be equal to minus 1 times S squared plus 2S plus 2 plus S plus 1 times K2S plus K3. And so this is just multiplication of polynomials. It's all it boils down to. So S equals, let's start to see if we can do this all together. I don't know how good you are in your math. I'm going to get an S squared term from this. And over here, I'm going to get an S squared term when this multiplies this. So I'm going to have a minus 1 plus a K2. That's going to be my S squared term. Then I'm going to have an S term, and the S term is going to be the 2. There's my 2. And over here, I get an S term when this multiplies this. So that's K3. And then when this multiplies this, that's K2. So there's my S term. And then the constant term is that 2 plus this times this. And often when we do this, there's redundancy in here, which I like from a safety factor so we can see whether or not perhaps we made any mistakes. And so what we're doing is we're matching the coefficients on the left-hand side of the equation with the coefficients on the right-hand side. I'm going to remind you the left-hand side looks like the following. 0, S squared plus 1S plus 0. And that's equal to minus 1 plus K2 S squared plus 2 plus K2 plus K3 times S plus 2 plus K3. There are 3 equations here. Equation number 1, 0 equals this. I hope you like that because we can solve for that immediately. And oftentimes these fall out pretty nicely for us. So K2 is equal to 1. Look at this one here. 0 is also equal to 2 plus K3. So K3 must be minus 2. So we don't have to check the middle one, but I just want to show you that it works. 1, this coefficient must be equal to this, is equal to 2 plus K2 plus K3. Let's make that a check. Is it? Well, let's see. 2 plus K1, 2 plus 1 plus minus 2. It sure is. Check. Okay, so one of those is just a redundancy check. We didn't need that. And that will typically happen. So we have the values of K2 and K3. So now I'm going to put them all together into the equation. So this is what we have. We have f of t equals minus 1 over s plus 1 plus 1s minus 2 divided by s squared plus 2s plus 2. Now, the first thing we have to do is we have to recognize that this denominator is indeed a form that we know. So this requires you to be proficient in mathematics because we have to manipulate to get this into forms that we recognize. That's what I'm going to be doing. I'm going to be playing the manipulation game. So the first thing I'm going to do is I'm going to recognize that this is s minus 2 over s plus 1 squared plus 1 squared. And if you don't know how to do that, you need to learn how to do that. Please let me know if you don't know how to do that so I can teach you how to do that. So once we're in that form, we still look at this and we say, you know what? I recognize the denominator in some of those partial fractions that we were looking at before in our table. So in our table transform, so recall s over s plus a squared plus omega squared. Inverses into e to the minus at cosine of omega t. We didn't do these for nothing. We did them because they're important. Omega over s plus a parentheses squared plus omega squared transforms into e to the minus at sine of omega t. This is neither one of them. It's a combination of the two. So this is what you have to do. You have to start with the s term. Start with the s term. Look at this number here. It's 1. And so what we have to do is we have to start with the following. So I'm going to expand the numerator. So the first thing, because there's an s there, I have to make it look like this. And because there's a 1 up here, I have to have a 1 there. So right now, I have s plus 1 in the numerator. But up here, I don't have s plus 1, I have s minus 2. So I have to make the numerator the same numerator. So in order to make s plus 1 the same as s minus 2, I have to subtract 3. Is that correct? Minus 3. But I want this number over here to match this number. So I have to make this number the number 1, which happens to be multiplied by 3. So I'm writing it that way. Okay? So what we're doing is we're making this in parentheses, it must match this. This number here must match this. And now this 3 that we have here and this 1 that we have here are just scalar multipliers using the linearity property. So watch me expand now. All of this equals minus 1 over s plus 1 plus s plus 1 over s plus 1 squared plus 1 squared. And then I have minus 3 times 1 over s plus 1 squared plus 1 squared. Now I recognize everything. I'll slide this down a little bit so you can see at least the sine and the cosine right there. So therefore, and I wrote f of t here. This was a huge goof. It's not f of t, it's f of s. Therefore, f of t equals inverse of the first term minus e to the minus t, inverse of the second term, e to the minus t cosine of t. Inverse of this next term would be minus 3 e to the minus t sine of t. And that would be our answer. And I can tell I made a math mistake somewhere in here in terms of numbers. The process is the same. These two should have the same answer, and I don't see the same answer. So that tells me that I made a mistake somewhere in the math, and I'm not exactly sure where that mistake is. But it could possibly be right here. I bet it's right here is where it looks like. 2 plus K2. That's where it looks like there's a mistake. I think there's a sign error in there somewhere. But don't focus on the sign error. I just want you to focus on the process. It's the process. Okay? So that is a second way that you can do it. Another thing that you could do with the partial fraction expansion is that you can do this. So we get to this point where we had f of s, it was equal to minus 1 over s plus 1, but we still had plus k2s plus k3 over s squared plus 2s plus 1. And don't forget what f of s was equal to. So let's put in what f of s was equal to. This was s, if I remember correctly, s over s plus 1, and then s squared plus 2s plus 1. So another approach is very similar to the approach where we set s equal to minus 1 or s equal to minus 2. This is an equation, and this equation must be true for all values of s. So what you can do is you can use two really good choices for s to be able to solve these values. I'm going to give you an example. S equals 0 is always an awesome choice. Well, when s equals 0, what do we have? On the right-hand side of the equation, we have minus 1 over 1 plus k3 over 1, and that's going to be equal to, look at the left-hand side of the equation, 0 over 1 times 1. So all of this is equal to 0. Clearly, k3 must be equal to 1. And that'll tell you immediately that was an error. I told you that was where I thought that mistake was, from that minus 2. So that's solved immediately for k3, and then you pick another value. But what you can't do is tell me a value that I can't pick for s. What value can I not pick? We always want to choose nice values. What value can I not pick?
-1.
Excellent, Connor. Can't choose -1 because we know it's going to cause that denominator to be equal to 0, which agrees with that term over there as well. So another nice number is +1. That's a simple one. So use easy numbers. So 1 over 1 plus 1, 2, 1 squared plus 2 times 1 plus 1, 1, 2, 4 equals -1 over 2 plus k2, which we don't know, times 1, so that's k2 plus k3, but we already have k3. K3 is 1 divided by 4. And now we just Obviously, we have one equation. The only unknown in this equation is equal to K2, and we just solve for K2. So we have 1/8 equals minus, let's put this over 8, minus 4/8 plus over 8, 2K2 plus 2. So set the numerators equal 1 equals minus 4 plus 2K2 plus 2. Minus 4 plus 2 is minus 2. So 1 equals, bring the minus 2 to the side, 3 equals 2K2 if I did that quickly. So therefore K2 would be equal to 3/2. So I don't love this approach. And the reason I don't love the approach is because oftentimes it doesn't get you anything a lot quicker. Oftentimes it doesn't get you anything a lot quicker. What it does get you is it gets you to be able to avoid complex numbers. That's what it gets you. Let's look at another example. (12s) plus 100 divided by s squared plus 6s plus 25. So we would have to factor this to know that there are complex roots. If you don't know how to look at that quickly and see that there are complex roots. So there are s plus 3 squared plus 4 squared. Okay, in case you're wondering how I do this, this number is half of this number. This number, or the number 4 is the square root of this number here squared subtracted from 25. So it's 25 minus 3 squared. That's where the number 4 comes from, if you're wondering where those numbers come from. Okay, so we've got this in the form. That's the second form that we showed. I happen to like this form, as I said. So what I want to show you is, first of all, there are no K values in here. I just want to show you how to work with these to get them in the form of the sines and the cosines. So again, what we're going to do is we're going to expand the denominator here, expand the size of the fraction, s plus 3 squared plus 4 squared. So we know here there are 12 s's, but I need s plus 3. So because there's an s here, there must be an s here. You can't make one up. That's how I know I have to have an s, because there's an s up here. But there are 12 of them, so I need 12 of them. So this 12s, when I multiply through, gives me 12s, scratch pad, gives me 12s plus 36. But I have 100. So I need to add some more than 36. So I need to add 64 more. But I don't want the number 64 here. I want the number 4 there. So this is 12 times s plus 3 plus 4. Now 64 is what times 4? 16 times 4 over s plus 3 squared plus 4 squared. And now we recognize perfect. Let me now break it up into the two fractions that I know. 12 s plus 3 over s plus 3 squared plus 4 squared plus 16 times 4 s plus 3 squared plus 4 squared. And this is equal to, don't need to expand it anymore. It's exactly the way we want it. So let's find the inverse. Let me help you. I'll help you with the hard part. 12. What's the inverse of this? That contributes to the exponent. That contributes to the frequency of the cosine. It's a cosine because we have the s plus 3 in the numerator. So this is e to the minus 3t cosine of 4t plus 16 e to the minus 3t sine 4t. Just a couple of notes. These are notes. You don't have to know this. You don't have to do this. A lot of people will do the following. They'll factor out the e to the minus 3t. Okay? Then they'll write this. 12 cosine of 4t plus 16 sine of 4t. Some people will factor a 4 out of here and leave this as a 3 and then a 4. You don't have to do that. Other people will take these two, now that they've done it in this form, they will take the sine and the cosine. And if you remember correctly, I told you that A times the sine or the cosine of omega t plus B times the sine of omega t. Do you remember that that can be transformed into the square root of A squared plus B squared times the cosine of omega t minus the tan inverse of B over A. I don't know if you remember that. We showed that, showed how that was true. So all of this is exactly what we had in the very first process that I showed you with regard to these inverses of the two complex terms. It's a cosine with a phase shift, and it has an amplitude out in front. That's what it has. But this is the way I would leave it if I were you. Don't touch it, leave it just like that. That's beautiful. Okay, let's do one last example just to show you that all the numbers in the world don't always turn out real nice. Sometimes they're ugly, but the process is the same. Example, f of s equals 4s plus 1 divided by s squared plus 4s plus 9. So when we take a look at that, I can recognize pretty quickly that this has two complex conjugate roots. If you don't recognize that, don't worry about it. This is equal to 4s plus 1 over s plus 2 squared. Remember that 2 is half of 4 plus, and then it's going to be the square root of 9 minus the 2 squared. 9 minus 4, which is going to be the square root of 5. Oh, goodness gracious. Plus the square root of 5 squared. Notice I always want this form in the denominator squared, squared. So I didn't write plus 5. I wrote it plus the square root of 5 squared. So sometimes it's ugly. There's no guarantee that it's always pretty. Sometimes it's ugly, but you're just going to deal with it. You're going to stand in there, be tough, because you can handle these numbers. They're only numbers, and we work with it. Okay. Bummer. It doesn't like when I rest my hand on the pad. Let's just open this up. A little bit faster would be nice. Okay, right there. So what do we have here? Well, the first thing is we're going to try to take this fraction, and we're going to expand it into a handful of terms that are in the form that we like. So first things first, s plus 2 squared plus the square root of 5 squared. Okay, in the numerator, we have a 4. Right there, there's a 4, but I want s plus 2. I have to have an s plus 2 because of that s right there. The s forces me to have an s down here. But there are 4 of them. So right now that's 4s plus 2, that's 4s plus 8. But I have 4s plus 1. So I have 4s plus 8, so I better subtract 7 of them off. So far, everybody like that? Now, I don't want that. I want something times the square root of 5. So watch what I do. I'm going to multiply this by the square root of 5 over the square root of 5. And now I'll rewrite it one more time. 4 times s plus 2 minus 7 over root 5, which we don't like, but I'll change that afterwards. But all of that multiplies the square root of 5. And so I just want to continue to remind you, all I'm doing is mathematical manipulation to get it in the form that I recognize. That's what we're doing, getting it in the form that we recognize. Most people would write that in a different way, so let me go ahead and do that. So it's 4 times s plus 2 over s plus 2 squared plus root 5 squared, root 5 squared, minus 7 root 5 over 5 times square root of 5 s plus 2 squared. I wrote minus here, that's a plus root 5 squared. Beautiful, we're all set. F of t equals 4 e to the minus 2t cosine square root of 5t minus 7 root 5 over 5 e to the minus 2t. Now cosine, sine, sorry about that, sine of root 5t. And there you have it. Okay, we finished 2 of the 3 cases that we need to cover. So when we're back together next time, what we're going to do the next time is we're going to go through the 3rd case. And the 3rd case that we have is a case of repeated roots. So what happens if I have in the denominator s plus 1 squared or s plus 5 cubed? How do we handle that in a partial fraction expansion? So we'll take a look at that. We'll have all 3 of our situations. And with those 3 situations, what we'll be able to do is we will then be able to find the inverse Laplace transforms of all of the functions that we're going to run into from our circuits. Let me give you some of the problems that I'm going to assign on homework. I'll pull up my pad again and give you the problems. For those of you who want to get a start, if you want to get a start, you can work on the following problems. So let me just share this again. So we have homework. And this is going to be, we're in chapter 12. And that is going to be on page 477. And there are not a lot of great problems here. There are some. 2, 8, 10. Those should apply more to the properties and finding the Laplace transforms and things like that. And then these following problems, 40, B and C. You can do A, B, C, D if you want to, but for homework, I'm assigning just these. And these are just partial fraction expansions. Find them, find the inverse Laplace transforms. So I think that'll give you plenty to do. This is more of a mathematical operation is what we're doing. There's very little here that revolves around circuit theory. But next week we're going to finish this off, and then we're going right into circuits. How do we Laplace transform a circuit? How do we work in that Laplace domain? We know how to find the inverse Laplaces. How do we find our time domain functions for voltages and currents? We're going to do all of that next week. Any questions before we part ways for the weekend? Okay, one of the things we should talk about next week is our final exam. Since it's just about 2 weeks away, we should talk about the final exam in terms of the day, the time, all of that. Until then, have a great weekend. Have a safe weekend. Please be safe. Please stay away from people and be smart. I'll see all of you on Monday.